We live our lives carried along by an invisible current, time. It flows in one direction, pulling us from birth through the seasons of our lives toward an inevitable end. We see it in the turning of leaves, feel it in our bodies as youth gives way to age. This forward march seems as certain as the rising sun, the silent metronome of existence. Think of a seed, it grows into a tree, a process that can't be reversed, just as we can't rewind our lives. A word once spoken, an opportunity missed. These are moments locked in the past. This one-way journey is what we call the arrow of time, pointing relentlessly toward the future. But is this the whole story? Is time's one-way flow just a limitation of our perception? The world we observe is the macroscopic world, the realm of big things. Beneath it lies the quantum world, where the rules are far stranger. Here, particles can be in multiple places at once, and the laws seem to bend. Scientists are beginning to question the arrow of time itself at this fundamental level. What if, deep down, time can flow both forwards and backwards? This isn't just fantasy, it's a possibility suggested by the very mathematics that describe our universe. Our most basic assumption about reality might just be a beautiful illusion. Picture a glass of milk teetering on a table. It falls, shatters, and the milk spreads in chaos. We see order turning into disorder, an increase in entropy, the hallmark of time's arrow. We never see the reverse shards reassembling, milk leaping back into the glass. This one-way process is everywhere. An egg cracks, a log burns, a star explodes, irreversible events. The past is where the milk was whole, the future is where it spilled. Yet, here's the paradox. The fundamental laws of physics don't care about direction. The equations that govern planets, light and atoms work just as well forwards or backwards. Film the planets orbiting the sun and play it in reverse. It still looks natural. This is time reversal symmetry, at the heart of our most successful physical theories. So why does our world, built from time-symmetric particles, display such a strong arrow of time? How can a universe made of reversible building blocks run down like a clock? This is one of science's deepest mysteries, a puzzle connecting the tiniest particles to the fate of the cosmos. The contradiction between microscopic symmetry and macroscopic irreversibility remains unsolved. Our experience screams forward, but the universe's rules whisper either way. Where then does the arrow of time truly come from? The universe's fundamental rules are remarkably even-handed about time. Newton's and Einstein's equations for gravity, for example, work perfectly whether time runs forward or backward. The same is true for electromagnetism. Maxwell's laws don't care about direction. A light wave from a star to your eye follows the same principles as one going the other way. This symmetry is a cornerstone of classical physics. Even in quantum mechanics, the Schrödinger equation is time-symmetric. Know a particle's state now, and you can calculate its past or future. The equation itself has no built-in arrow of time, yet our reality moves only one way: aging stars, decaying organisms, irreversible processes. It's as if a hidden rule breaks the symmetry, forcing time to flow forward. Where does this hidden directive come from? To find time's arrow, we must peer into the quantum realm. No particle is ever truly alone. It constantly interacts with its environment. Imagine a snowflake falling, buffeted by air, warmed by radiation, pulled by gravity. This is an open quantum system, the object of interest plus everything it interacts with. These interactions are crucial. They cause strange quantum behaviors to fade as we scale up. A quantum particle can exist in multiple states, but this superposition is fragile. The slightest interaction with the environment collapses it into a definite state, a process called decoherence. Decoherence bridges the quantum and classical worlds, making quantum processes appear irreversible. Every interaction leaks information into the environment like footprints in sand. Once lost, this information is practically impossible to retrieve. This is the traditional explanation for time's arrow. Decoherence creates the one-way flow we observe. The spilled milk can't unscramble because its information is scattered among countless atoms. But recent discoveries are challenging even this idea. Is decoherence really the source of time's arrow? Physicists at the University of Surrey and the International Institute of Physics in Brazil took a fresh look at open quantum systems. Conventional wisdom said that environmental chaos breaks time symmetry, cementing the arrow of time. But their analysis revealed something astonishing. The fundamental time symmetry remains, even in open systems. The equations describing evolution work forwards or backwards. The arrow of time isn't forged here after all. The irreversibility we see may be a result of our limited perspective, not the laws themselves. The mystery of time's arrow goes deeper than we thought. The Surrey team focused on a mathematical tool called the memory kernel, which describes how a quantum system's past influences its future. Traditionally, physicists thought the memory kernel was inherently asymmetric. Past affects future, not vice versa. This was believed to break time symmetry and create irreversibility. But the researchers challenged this, constructing a time-symmetric memory kernel. To their surprise, the math worked. The environment's influence could be perfectly reversible. The memory of the system is not a one-way record, but a conversation between past and future. The memory kernel, once thought to shatter symmetry, actually preserves it. This doesn't mean time flows backward, but it keeps the possibility open at the most fundamental level. The secret of time's arrow must lie elsewhere. The search continues. The researchers found something stranger, a tiny mathematical discontinuity at the moment an interaction begins. It's like a switch being flipped before. System and environment evolve independently. At the instant of interaction, a unique signature appears. This discontinuity is nearly invisible, but it distinguishes the start of the process. It acts as an initial condition, making forward evolution seem natural and reverse seem impossible. Yet if you run the equations backward, the same discontinuity appears at the new start. The forward and backward journeys are perfect mirror images. The discontinuity isn't a flaw. It's what makes symmetry possible in real interactions. The arrow of time may be tied to how we perceive events as having a definite start. The spilled milk story begins when the glass tips. That starting point shapes our sense of time's flow. But the underlying physics still allows the story to be told in reverse. If the universe's laws are time-symmetric, our sense of time's one-way flow may be an illusion. At the quantum level, time might be a vast frozen landscape. Past, present and future all equally real. Our consciousness moves through this landscape, creating the illusion of flow. Could there be places where time runs backward, inside black holes or at the Big Bang? The laws don't forbid it. We may simply be blind to other possibilities. If we learn to control quantum systems, could we exploit time symmetry? Perhaps even reverse quantum errors? These ideas are speculative, but understanding the rules is the first step. The universe may be grander and stranger than we ever imagined. Our journey from spilled milk to quantum equations reveals that time's arrow is not a fundamental law, but an emergent property. The universe's basic rules are symmetric, allowing the dance of particles to run in reverse. The Surrey team's work shows that even with environmental chaos, time symmetry can be preserved. The irreversibility we see may be a feature of how we observe, not a flaw in the system. This challenges our assumptions and reshapes our understanding of reality. If time is more flexible than we thought, it could change our theories of cosmology and physics. The nature of time remains one of science's greatest mysteries. With each discovery, we wade deeper into the unknown. The universe is a place of hidden symmetries, where the past may be a reflection of the future. The journey to understand time is far from over, and it fills us with wonder.